Hi all, the problem that we are going to solve today is search and rotated sorted array. We are given an integer array which is sorted. We are also given target. We are asked to find the index at which this target falls. But we are given that we are given that this array is rotated at some point. So this is what rotation means. If this array is rotated at 0.4, which means that the elements including 4 and to the right of 4 are shifted to the front of the array. So if the target is found, we just need to return its index. If not, we will just return -1. So here the target is 0 and here it falls at index 4, so we return 4. In both these examples, we do not have the target in both these arrays, so we return -1. It is also given that all the elements are unique, so we will not have any duplicate values, and we are given it is guaranteed to be rotated at some pivot. So the normal approach would be to just traverse through the entire array and search for the target. We can also the optimized approach is binary search, but the only problem is that this array is rotated, so we will have some edge cases. Let's see how we can handle them. So in a normal sorted array, the elements are in increasing order. Graph would be something like this, but in here we have two parts with two parts in which the elements in the first part are greater than the elements in the second part. But if you see in normal sorted array, the elements in first part are less than the elements in second part. If you break the array into two parts, the elements in the first part are always less than the elements in the second part. But in rotated sorted array, which is rotated at some pivot, so the elements in the first part are greater, all the elements are greater than all the elements in the second part. So the lowest in the first part is greater than the highest in the second part. So we can do one thing. We can just try to find out the index at which this array is rotated. How we can do that is just we need to do a binary search. We can try to find the mid and compare its adjacent elements, compare its neighbors. So if let's say that my mid falls in here, and if I compare its neighbor, I see that it's greater than my mid. So this will not be the element in which the array is rotated. At some point I will come to an element in which the neighbors is less than this element. So I will come to know that this is my pivot at which the array is rotated, and then I just need to find out if my target falls in between this pivot and the beginning, or between this element to the right of the pivot and the end. Once I know in which part my target falls, then I can just do a normal binary search, because both the parts are strictly increasing, but not the whole array. Each of the parts are strictly increasing, they are not rotated. That is one way. Another way is, so if we try to find the mid of whole array on a high level, there are two cases possible. One is my mid falling in the first part. I will have my mid in first part. The second case is my mid falling in second part. I can have my mid, the mid may fall in second part. So let's see the first case where my mid falls in first part. So let's say that my mid is somewhere here or here, or it can also be here, because we are taking the floor. So my mid can be L or somewhere between L and R, but never R. I mean to the right, the end of the array, unless there is only one element. So mid can, let's say our mid is here, so I need to find out. So if my mid is here, and again this whole array is broken into two parts, one part is non-rotated and one part is rotated. So I need to find out which part is rotated and which part is non-rotated. So how can I do that is, I can compare my beginning or end. I can take any of them to compare my mid. So if I take the beginning, so if you have a array in increasing order, you take any element and you compare it with beginning, it will be always greater. Or if you take the end and compare my mid with end, it will be lesser. My mid will be lesser than the end. So we will use the same logic to find out which one is strictly sorted. So I will compare my mid with beginning. In this case, if it is greater, I will know that the array to the left of my mid is strictly strictly sorted. It's non-rotated, and the array to the right, the rest of the array is rotated. So once I know that this is which part, either to the left or to the right, is correctly sorted and non-rotated, I can just try to find out if my target falls in this array or not, in between these two, mid and beginning. If it does not fall in here, I then just need to go to the right, and this problem becomes a sub-problem of the original problem. If it does fall in here, it's a normal binary search. So there are two cases here. My target falling in, target is less than mid. This is my sub case, and the other case is my target falling in, where I need to go to the right, greater than mid. Here also we'll have two sub cases. If my mid falls in second part, I compare my mid with beginning. If it is greater, then I will come to know that so here I can just use else. If it does not fall on first part, it does fall on second part. If my mid, if I compare my mid, if I compare my mid with beginning, if it is less than, then I know that it falls in second part. So here I will have two sub cases. So I now that I know this is strictly increasing sorted, this is sorted and non-rotated, because I know that this mid is less than my start of the array, and the array to the left is not rotated and array to the right is non-rotated. So I'll just compare, I'll just try to find if the target falls in between this mid and end of the array. If it does fall, I go to the right. The second case is I go to the left. So these are the four cases that we need to handle on high level. So the mid, let's recap. The mid can either fall in this first part or the second part. If it does fall in the first part, I compare my beginning. But how will we know that it does fall in the first part? I compare my mid with the beginning of the array. If it is greater than the beginning of the array, then I know that it does fall in the first part. And if my mid is less than the beginning of the array, start of the array, I know my mid falls in the second part. If my mid falls in the first part, then I I know the array to the left is sorted, then I try to find if my target falls in between in this array. If it does not fall, I go to the right. If it does fall, I try to search in this array. In the second part, the same cases, I try to find if my target falls in between this mid and end. If it does fall, I go to the right. If not, I go to the left. Let's try to code this. So we'll do a dry run once after coding. It will be much clearer then. So I will have 2 pointers. One is left and the other is right. And until my left is less than or equal to r. For first case is to find out if my mid falls in the first part or not. So if my mid is, I compare my mid with the beginning of this array. So let's so here we can take this example. So my mid comes out to be 7. So I compare my mid with 4. So it is, my mid is greater than equal to nums of L. So if my mid is greater than or equal to nums of L, I know that this part is sorted. Array to the left is sorted. If not, if it does not fall, if it is, let's say my mid comes out to be 0 and I compare my mid with 4, it is less, so I know the array to the right is sorted. So I'll have 2 cases. One is this and the other is this, falling to the right. Okay, I will also I will need to handle equal to, if my nums of mid is equal to target, I can just return the mid index. So this case is my mid falling in the first part. So if my mid falls in the first part, I just need to see if my target falls in between beginning and mid. If it does, we just need to go to left. If it does not, we need to go to right. If not, okay, this is the case where my mid falling in the second part. So I now need to check if my target falls in between mid and end of the array. If it does, I need to go to the right. If it does not, I need to go to left. So these are the 4 cases. So this one case, second case, third case, fourth case. So let's see this. So if my mid falls, my mid comes out to be 7 initially when considering the whole array. I compare it with my start of the array. It is greater than 7. So this condition, it comes under this condition. And I try to find if my target is greater than or equal to if it falls in this area or not. Between 4 and 7, yes, it is equal to 4 and is less than mid. So I will just go to the left. So r equal to mid minus 1. So now we are left with this array. So mid falls to be 5, then mid comes out to be 5, and I try to compare my beginning, which is L, with the mid. It is, my mid is greater than star. Again, it comes under this condition. So I try to find if my 4 is greater than or equal to nums of L, it is equal to nums of L, and is less than mid. 4 is less than mid. So again I go to left. So we are only left with 1, and this condition will be met. Nums of mid equal to target after just return the mid. So if I could not find the element, I will just return -1. So let's try this. Okay, so the runtime complexity will be of log n, and we are doing a binary search only once, unlike the other approach wherein we first try to find the pivot and then we can do a binary search to find the target. Space complexity will be O of 1. So try this, try both the approaches, wherein you try to find the pivot and search in correct sorted array, and try this approach as well. As you can see, I have tried it many times. I have submitted it many times. It took some time for me to clearly internalize this logic. So yes, let me know if you have any comments.